All right, hopefully you took a lot of time to experiment with Desmos and play and try to make some of the discoveries that I'm going to use down here. But let's get through these other ones first. So solving for x looks like a job for an arrow diagram. So we'll start with the x, and we will multiply by -4, and then add 3. Get that into the denominator with the reciprocal function, multiply by -2, and add 6, and that's supposed to get us to -2/5. Okay, so subtract 6 coming that way, divide by a -2, flip it over, subtract 3, divide by -4. So -2/5 minus 6, that's 30/5 is the same thing as 6, so that's -32/5. Divide that by -2, and that's going to give us a positive 16/5. Flip that over, it becomes a 5/16. Minus 3 is 48/16. 5 minus 48 is -43/16, and divide that by -4, and we're going to get 43/64 as an answer there. Okay. All right, double check, multiply by -4, add the 3, flip it, multiply by -2, add 6, get -2/5. Okay, subtract by, yep, agree with that. Draw pictures to show the graphical difference between a root of multiplicity 1 and a root of multiplicity 2. A root of multiplicity 1 will look like this, something like that when it goes through so this is my multiplicity 1. A root of multiplicity 2 will look something like one of these. Okay, so these are possible roots of multiplicity 1 here. These are roots of multiplicity 2. They touch the axis but then turn around and go the other way. All right, zeros, vertical asymptotes, holes in behavior, sketch a graph. Zeros come from the numerator. That is going to be 0 at 3/2, at 2, and at 1. The vertical asymptotes come from the denominator. That's a 3, a -1, and a 2. Places where there might be a hole are where there is an argument between zeros and vertical asymptotes, which means that 2 is not a 0 and it's not a vertical asymptote. X equals 2 is where the hole is. And the end behavior of this graph, this in the numerator is a 2x cubed, and the denominator is an x cubed, which reduces, simplifies to a 2. So this is a horizontal asymptote. At 2, or I could write that the limit as x goes to either positive or negative infinity of this function is 2. So if I said that this was 2, I know that's where I'm going to end here. I cross the x-axis at 1 and at 1.5. According to those, I have vertical asymptotes at 3 and at -1. So this function must come in this direction and then turn and go up the vertical asymptote. There's nothing special about that vertical asymptote, so it's going to come in here, it'll cross there, stay above the x-axis just briefly and cross there, and then back down this asymptote, and then back here and out this direction. It did say that I had a hole at 2, so I'll find where x equals 2, and indicate that there is a hole there. All right, my zeros here are going to be at x equals 4/3 and at -2. My vertical asymptotes are going to be at +2, and I'm going to indicate that there was a multiple root there, so that's going to change the shape of the graph. And at -1, there are no holes because the same number didn't show up in those lists. My end behavior, if I multiply these together, this is going to be a -3x squared over, this would give an x squared times an x, that's an x cubed, which reduces to a -3 over x. 1 over x with a negative leading exponent will have a graph like this. So my limit as x approaches both positive and negative infinity of g of x is 0. And so horizontal asymptote at 0, and I know it's on top over here, and it's going to be finishing below over here according to the information from that. It crosses at -2 and at 1 1/3. I have a vertical asymptote at 2, and it is a double because of this squared here, and a vertical asymptote at -1. So if it's going to be over here, close to 0, it's going to have to come in. It has a place to cross the x-axis here, so it will. And it will do that. Because this is a normal asymptote, it will then come down this direction, over to here, turn and come down here, and because it's a double asymptote, it's going to start from down here again and go up and end out that direction. Okay. Kind of ran into my other graph there a little bit. See if I can separate those a little bit. This one's coming down there and there. This goes that direction right there and has that vertical asymptote. Okay. All right, here my zeros come from the numerator. I've got a -2, and it is a double, or it's actually a triple, so I'll have to pay attention to that. And I've got one at 1 and at 3. My vertical asymptotes, I've got one at 2, and it is a double. And at 4, no duplicate numbers in those lists, so no holes. My end behavior, this would be x cubed times x times x, that'd be x to the 5th over x squared times x is x cubed. That reduces to an x squared. That parent function has end behavior that looks like this. So the limit as x approaches both positive and negative infinity of h of x is positive infinity. So let's mark things up here. I've got a 0 at -2. That is going to be a triple root. I'll show you what that looks like. 0 at 1 and a 0 at 3. A vertical asymptote at 2, that is a double just like the other one was, and a vertical asymptote out here at 4. My end behavior, it says it's going to start up here. So starting up here, coming down this direction, this was a triple, so it actually is going to come down and it's going to wiggle its way through the axis a little bit. It will cross because it's odd, and it goes down here a little ways, but there's a place to cross the x-axis up here, so it has to turn at some point and come back up through there, and then the next thing it runs into is a vertical asymptote, so it has to do that. This vertical asymptote was a double, which means it's going to start on top here on this next one. It's going to come down. There's a place to cross the x-axis, so it will. And then the next thing is this vertical asymptote, which was a normal vertical asymptote. So instead of staying on the same side of the x-axis as I was, it's going to jump to the other side. There is no place to cross, so the in behavior starts to take over, and it ends up doing that on that side. All right. A rational function that would generate the graph at the right. Well, let's see what I've got going here. It looks like I cross at 1 and at -1, and at +3, and those are just singles. It looks like I have a vertical asymptote here at -2, but it's high on both sides, so that means it's a double. This vertical asymptote at +2 is just a regular one, and it looks like I've got a horizontal asymptote at about 1. Okay. So 3 zeros, 1, 2, 3 on the vertical asymptotes. So because it crosses at -1, I must have an x plus 1. Because it crosses at +1, I must have an x minus 1. Because it crosses at +3, I must have an x minus 3 in the numerator. And the denominator, because I have a vertical asymptote at x minus 2 or at -2, I must have an x plus 2. And because it's high on both sides, it must be squared. And I've got this other one at x equals +2, so it means I have an x -2 there. Checking, I would end up with a x cubed over x cubed, which reduces to a 1, which accounts for where my horizontal asymptote is. Right there, I could even double check. It looks like where my y-intercept is here. If I put zeros in for all of my x's, I would get a 1 times -1 times -3. That would be a +3. 2 squared is 4. 4 times -2 is -8. It says my y-intercept should be about -3/8. Yeah, I believe that. That looks like it's right about where that is. So this is what that equation should look like. All right. If the following is possible, then write a rational function that would accomplish it. If not, explain why it isn't possible. Okay, we have a function that has zeros at -5 and 5 and a 0 of multiplicity 2 at 0. So we said this was -5 and 5 across here, and we've got something special going on there. It also has a vertical asymptote at -3. Okay. And one of multiplicity 2 at x equals 3. Let's see, this was my 0 here. So special asymptote there. X equals 6 is not in the domain, but there isn't an asymptote there. There must be a hole here, wherever the graph happens to be. And the in behavior matches the in behavior of 1 over x. So 1 over x has in behavior that looks like this. So it would have to start below the axis here. And this is the place where it crosses, so it would have to come down and would definitely have to do that. And then would have to start here and come up that way. Multiplicity 2 at 0, so it's going to bounce off of there and come down here. And that has a multiplicity 2 on that, so it would have to come up and cross here and do something like that with a hole in there. That would definitely match the behavior. The question is, write the rational function that would accomplish it. Well, let's see. I would have to have an x plus 5 in the numerator. I would have to have an x minus 0 squared, or an x squared. and then I would have to have an x minus 5. The vertical asymptote at negative 3 would be an x plus 3. The vertical asymptote there would be an x minus 3, and it would be squared. I would have to have an x minus 6 and an x minus 6 that would have canceled out. So that accounts for everything that's going on in those places. This would have in behavior, though, of, let's see, 1, 2, 3, 4, 5. This is x to the 5th in the numerator, and 1, 2, 3, 4. This is x to the 4th in the denominator. So the only way this would force the in behavior to be like x, which would be more like this than like that. And there's no place else that we can mess with things to make the asymptotes something more than what they are, unless we can't square that one. It would almost say that this, I think we could do it if the x plus 3 was cubed down here. It didn't say that we had that special thing going, but that would make this an x to the 6th and would give it the x in behavior of 1 over x, and it wouldn't change the behavior of the graph. So as long as we had that in there, then this should fit the description that we've got there. Okay. And just for fun, I'm going to try to put that into Desmos and see if we actually get that. So I've got an x plus 5, and I'm going to do the divided by and start to get some stuff going in the denominator here. X plus 3, we'll raise that to the 3rd power. Other stuff in the numerator is an x squared. Oop, not x to the x. Oop, not that either. X squared. And we said we also had an x minus 5 up there and an x minus 6. And with this x plus 3 cubed, I get an x minus 3 squared. And an x minus 6. All right, so let's zoom out a little bit and see what we've got. That looks pretty much like what I drew there. If we take this along here, at 6 it is undefined. The in behavior out here is approaching 0. In behavior out here is approaching 0. We cross at negative 5 or positive 5. My asymptotes are at x equals 3 and x equals negative 3. So I think that pretty much matches the description, and it required that the x plus 3, this asymptote, have a cube on it. All right, that is it for that one.